Now that we've updated our cutter geometry tool with a better method of applying that large scale noise, we can design the final shapes of our cutters and run our final fracture. Now these cutters are currently pretty low resolution. You can increase that cutter resolution here, or you could just add some mesh subdivisions. You can play around with the slight differences between using those interchangeably. In this case, I'm just going to add a few more subdivisions in here, and I'll turn that noise size down to 2 instead of 20. And I'll try increasing that noise amplitude. I often find that an amplitude that matches the noise size tends to be a pretty decent starting point, and then you can tweak it from there. You can see the same thing with the large noise size and amplitude as well. They're in a pretty similar ballpark to each other. Although in this case, I think I'll push that small noise amplitude a bit more. Maybe cranking it up to about 4 looks like a pretty decent result. Also, don't feel like you have to get all of your detail within that cutter geometry tool. There's no reason you can't do extra processing on that geometry afterwards. For example, if I'm pretty happy with how everything's looking, but I just want a little bit of extra detail in there, sometimes I'll just throw in a mountain sop after my cutter generator. In this case, I think values of 0.3 for both the element size and height work pretty well, and that just kind of roughens up that cutter surface just a little bit more. You could play around with the small noise settings and maybe add some more octaves to that, but I often find it easier to break up the different layers of detail into separate steps rather than trying to get it all in 1 or 2 noise passes. Alright, so now that we have some decent cutters, let's run our initial fracture on our geometry. So we'll drop in our shatter HDA, connect our geometry to that, and our incoming geometry already has good name attributes, which is pretty important for that shatter HDA per piece looping. And before we run this, we'll make sure to set a new pieces prefix here that matches what we're currently shattering. In this case, it's the exterior, so I'll just rename that so that all of our pieces have nice descriptive names, and I'll display that shatter to run it. So with just those few cutters, that was pretty quick. I think that was maybe about 5 seconds. Let's display an exploded view of that to see what all those details look like. And we'll definitely need to fracture up this geometry some more, but if we start to look at what these details are looking like, I'm pretty happy with the shapes of those features on the edges. That's all looking like some pretty convincing concrete detail, especially at the distance we're working with. It can be good to check the geometry from your actual shot camera to see how those details hold up at this given camera distance. Try turning that exploded view down lower. And at this camera distance, all of that detail looks like it's holding up quite well. So I think those noise settings will work pretty well for the first pass at this fracture. So I'll go back to the cutters and we'll generate a whole lot more of them. We'll see what maybe 30 cutters looks like. And I'm going to see if there are many areas of the geometry that are not covered by cutter planes, because we want to make sure this is pretty thoroughly broken up. Looks like we have a few pretty big patches in there. And you can play around with different seed values if you would like, although with such thorough cutting and so much detail in here, there's already a decent amount of randomness, so that tends to not be the most crucial setting unless you just really want to see variations of these similar cutters that you've already designed. Now, it's not necessarily problematic to have these patches here where we don't have cutters running through it. You don't have to have every single bit of this completely sliced up, and we'll be using some constraints later to create larger clumps of geometry anyway, but I think I'm going to go a little bit higher with the number of cutters here. In this case, I'll turn it up to 45. And I'll turn down this trim outside object so that it trims a little bit closer to the geometry that we're cutting. We'll just lower that expansion maybe to value of 3. It should optimize things a little bit. And then we can run our fracture again to see how this looks. Now this fracture took a bit longer to run, of course, since we had far more cutters slicing this up than just the small handful of cutters we were using before. But it looks like we have a pretty decent amount of fracturing going on, and it's not so tiny that we're losing any sense of interesting mid-sized pieces in here. To me, this looks like a decently balanced level of fracturing for our geometry. Of course, there are some really tiny little pieces in here that we won't necessarily want to simulate in our RBD sim, and we'll do some more optimization on this later, but it's good to cache out our fracture in this state before we do our optimizations. Before I cache this, I'm going to do a little bit of extra cleanup and processing. After running a fracture, I like to use a clean node to clean up any stray points from our fracture output. Sometimes you'll get some random disconnected points that aren't connected to any valid polygons, and on this clean node, by default this will remove those unused points. I do always turn off this remove degenerate primitives option because I find that that's overly aggressive with what it considers to be a degenerate prim. That can delete some small prims that are actually totally fine and valid and we don't want deleted. So I make sure to keep that off. It's pretty important. But we'll leave that remove unused points on, and if you compare our point count from the shader output to our clean node, it looks like that's removing, I think, 8 points that are apparently disconnected points. I'm also going to set the inside attribute like we did with our static geometry, so you can create a primitive wrangle for that. I'll call this set inside, and we'll make this run on the inside group from our drop down here. And in the vex, I'll type I at inside equals 1, so that only the polys in that inside group get that value of 1. And I'll do a quick sanity check in our spreadsheet to make sure that's working. It looks correct, and if you really want to be sure, you can do that visualizer check that we did on our static building as well. And now that we have this attribute set, we don't really need that group anymore, so I'm going to clean that up with a group delete. And at this point, there aren't any groups that we care about, so I'll just use a star and that group deletion there. And then we'll also add our rest data with the rest sop. Now, in addition to caching our fracture, we also want to save out the constraints that are generated in this fracture process. As I keep saying, in these first couple weeks, we will look more at constraints later, but for now, all you need to know is that these need to be saved as well. So I generally will create a null, connect it to that second output from the shader, and call this constraints. Now, it would be a bit annoying to save these out to separate caches, especially when you consider that we'll need to run the fracture and constraint generation on our window frames and interior as well. And if we were to just merge these together, then that would mix up all the attributes on them, and we wouldn't be able to cleanly extract them afterwards, because all these attributes and data kind of get jumbled together. But thankfully, Houdini 17 introduced a very helpful organizational SOP for this, and that's the RBD pack. I briefly mentioned this when we set up our shader HDA because we needed to use it in that loop so that we could output both the fracture and the constraints from the loop in a clean and contained way. And we're going to do the same thing here with our fracture caching. And if you hover over the inputs of the RBD pack, you can see that the first input is the geometry, the second will be those constraints, and the third is for proxies that we will generate later. And this will be nice and convenient for caching purposes. And then after the cache, if we want to separate those out again, we can just use our RBD unpack to separate out that geometry versus constraints versus proxies, and those attributes will not be all mixed up. Now, one of the nice things about fracturing multiple sections of our geometry like this is that once we've set up some noise values that work pretty well for our cutters on the exterior of the building, we can copy this whole setup and then use that for the interior as well. Even if you don't want to use the exact same values, this will work quite nicely, at least as a starting point for that interior portion. So I'll connect my interior to the cutter generator, and also connect that to the shader, of course. Now, this interior geometry occupies much more 3D space than the exterior does, so our cutter geometry is much heavier. We could optimize this down a little bit more by lowering that trim object. We can try lowering it to maybe 1.5. And if you zoom in on your geometry with cutters, it looks like we might be able to get away with lowering that trim a bit further. Maybe try 1. You always want to make sure that you still have that little bit of buffer just to reduce the risk of any partial cuts where the Boolean planes don't go all the way through the surface. But lowering that trim some more should help at least a little bit, because I found that with this larger interior geometry, we still need to use more cutters than we did with the exterior. Let's try increasing that to 65 cutters. If you want to, you could, change the seed to something else as well. Although, as I said before, you'll get a different scatter by piping in different geometry. So there's a whole lot of randomness here, and that seed tends to not be super crucial for this. And now that we've adjusted our number of cutters and trimming and seed, we can go ahead and run this shader and see what that looks like. This interior fracture was a bit slower than the exterior. It ran in about 3 minutes in my setup here, but that's actually not too bad if you consider that our cutter geometry is more than 3 million polys, and that's chopping up our interior into, if you look at the name attribute, this says, in my case, more than 72,000 unique pieces and almost 13 million polygons overall. So 3 minutes for an operation like that is really not too bad. For the window frames, you could run a detailed Boolean fracture on this, but for more simple geometry like this, it's often not worth it, and it's sometimes easier to just run a very basic Voronoi fracture. So for those frames, I'm just going to drop in a scatter to create some Voronoi points. And for this, instead of forcing a total count, I'm just going to use a density scale of 3. And I'm going to turn off the relax as well. You can test it with and without that if you'd like to see which distribution you like more. And then I'll drop in the Voronoi fracture SOP, connect our window frames to that and our scatter points. And for the naming, I'll switch this to append to the existing window frame names. And I'll add an underscore to the beginning of this piece so that it separates it from the existing names on that geometry. And everything else on that Voronoi fracture you can leave at the defaults. Although, I suppose we could turn off that outside group since we don't really ever need that. And then we can run that fracture. And that's a very quick one. Took about 10 seconds. And let's do an exploded view to check out our results. And this looks good. We don't need to have a super fine and detailed window fracture. As long as these are broken up into some vaguely interesting pieces like this, that will be good enough for our simulation. And although we've used a different fracture technique compared to the rest of the building, we can still use the same cleanup that we used for the Boolean fractures So I'll just copy that whole cleanup and post-processing section, paste that over for our window frames, hook up our geometry and our constraints, and now our window frames are ready to be cached out as well. Now to cache all of our various sections, I'm going to merge together the results of all 3 RBD pack SOPs. And I'll create my file cache, and I'm going to call this fracture unfiltered, because before we start simulating this, we're going to do a bit more filtering and processing on our final fracture results. And in the file cache settings, change that frame range to the current frame, and we'll go to our job location and our caches folder, building RBD, and I'm calling this geometry fracture unfiltered. And once you save that to disk, you can turn on the load, and we'll create a null to refer to this elsewhere in the scene. I'll just call this out fracture unfiltered.